All right, hello everybody. Thank you for joining me on the last day of NDC London. I'm Adrienne Braganza Tacke. I'm a senior developer advocate at Cisco. You can ask me more about that later, Cisco or why developer advocates at Cisco. And today I'd like to talk to you about idempotency. So this talk came about because, like a lot of my talks, they come about from talking with my husband, who happens to be an architect. So we're both a developer, we both talk about really nerdy things, we talk about problems at work, we try to solve each other's problems that we have at work, and these kinds of topics occur very, very often. And one thing that was very interesting to me is that the scale with which he works for Amazon, the scale that he works at is mind-boggling to me. He works at 100,000 transactions per second. And this is going to keep happening because I don't have my power adapter. But we'll get through it a little bit quicker. So the scale with which he works at is mind-boggling, 100,000 transactions per second, concurrent requests per second. And as we start talking about these kinds of problems, we naturally started talking about what did it take to kind of run these kinds of systems? How do you actually handle hundreds of thousands of transactions per second? And as the other things are natural, idempotency came up. Idempotency is the key to the one serverless principle, really any principle in any good architected system, to rule them all. So the very quick agenda, we're going to talk about idem what, because a lot of people are like, what is this word? I've heard of it. I think I know what it means, but when you ask me to explain it, I can't really explain it. And then we're going to talk about why serverless and idempotency go hand in hand. Then we'll talk about safe retries, and finally we'll talk about how you can achieve idempotency through a couple libraries that I've found, as well as a couple APIs that help you use idempotency in your applications. So idem what? Who here has heard of the word idempotency? Okay, so we can finish this talk, right? So how do you pronounce it here? Is it idempotency? Because other people say it's idempotent, idempotent.
It's usually the first syllable that gets stressed.
Right, idempotent. So here, when I started looking up the actual words that were recorded, idempotency, I'm going to say it idempotency because I'm the American here. Idempotency is actually not a word. It is not a real word. And when I look this up in the dictionary, what you get is actually idempotent, according to Merriam-Webster. And Merriam-Webster says, relating to or being a mathematical quantity which, when applied to itself, under a given binary operation, equals itself. So as you can see, even me reading this definition, I'm already stumbling over my words. It's a little bit complicated, and in the great words of Kevin from The Office, why waste time, say a lot word, one few do trick. So I looked up a different definition, one that I could actually say, one that I could actually understand, and that is Random House Webster's, which is unchanged when multiplied by itself. So that makes sense to me. That comes from that mathematical quantity or quality of idempotency of whenever you multiply two inputs, they usually come out to the same output. And so this can very easily map to what we understand when we are trying to build applications in an idempotent way. Idempotency, a little bit revised, is a characteristic that ensures when running an operation over and over and given the same input, so mapping that to when multiplied by itself, that the same output is achieved every single time. It is unchanged. That means no matter how many times you run an application, no matter how many times you send an event or invoke an event, no matter how many times you retry something, if you send the same inputs, it should always give the same output. And that is essentially idempotency. So keep that in mind as we go through the rest of this presentation. So at this point now, you're like, great, Adrienne, what does idempotency have to do with good serverless architecture? And I'm going to be one of those people that answers a question with another question. And I'll say, have you heard about the 7 design principles of well-architected applications? Who here has heard of that? Wonderful, you will learn something today. So, 7 design principles of well-architected applications. So because my husband works for Amazon, and also because AWS happens to be the market leader in cloud, we're going to borrow or shamelessly steal the 7 design principles of well-architected applications. And in this particular case, we're going to look at the serverless lens. So they have these principles, these best practices that you try to follow, and the lenses are very specific to a particular topic. So what are the 7 very, very quickly? First thing is speedy, simple, singular. This follows the single responsibility principle. You want to make things focused. You want to only do one thing at a time. You want to minimize execution time, and you want to do additional processing through a queue instead of waiting. Share nothing. So unless you use a very specific library that does this, you have to assume that your functions are stateless. So you have to start each execution as brand new, and you explicitly state and load what you need every single time. Third, you assume no hardware infinity. So at this point, especially with the serverless lens, there's a reason why you chose serverless, right? You don't care about what hardware you're using. So that naturally follows that when you're building applications, you don't want to build them in a way that depends on the hardware. So you chose not to deal with hardware, so try not to use code or dependencies that are hardware agnostic. Fourth is you use events to trigger transactions. So this is more about getting comfortable with asynchronous operations. So prior, we're probably used to, you send a request, you wait for something to happen, you get a result back, you do something onwards with it. And we're trying to get away from that. People don't need to wait for everything that happens in our system, and you should try to design it in that way. Get more comfortable with asynchronous transactions. You also want to think concurrent requests, not total requests. So it's not hard to see why people try to think of total requests. Sometimes that's the way that we're built. Sometimes those are the limits that we feel that we are in. But another thing that we tend to forget is how to take advantage of using serverless services. So think concurrent requests. Optimize horizontal scalability. Rather than the fewest number of requests, try to see where you're not taking advantage of concurrent requests. Next is orchestrate your application with state machines and not functions. So this is really biting at the fact that you don't want to invoke functions from another function. You don't want to have this tangled serverless spaghetti mess where you're saying, hey, do this, hey, do that. That's where something like step functions or durable functions come in, where you have an actual orchestrator who can take charge of all of that and see what is happening at the same time and make sure you're not invoking it directly from the single functions. And so out of these 7, the last one out of this serverless lens of well-architected applications, the 7 design principles, is design for failures and duplicates. So while almost all of these principles are affected by idempotency, the one that's absolutely impossible without it is this last one, to design for failures and duplicates. This is necessary because things are going to fail. It's been said, we know things are going to fail, and so because we know things are going to fail, we know that anomalies are going to happen, we need to design a system that incorporates the fact that we know things are going to fail. And knowing that means incorporating idempotency is key when we want to deal with these failures and duplicate requests. So, how do we deal with designing for systems that will have failures and duplicates? Well, one thing that we need to remember is that failures will almost always lead to retries. So how many of you have uttered the words, have you tried turning it on and off again? Yes. How many of you have said, just retry the function? How many of you have said, just recompile it? Yes. So failures often always lead to retrying something, and that is okay. We know that sometimes the edgiest of edge cases, sometimes the really weird things that happen will get fixed when we retry them. And so understanding that retrying is not a bad thing, that it's actually an effective solution to taking care of some of these problems, we want to know that doing retries is something that's going to be used. And retries are such an effective solution to some of these edge cases that they're actually being built into some of these libraries, as we'll see later. So now that we know that retries are going to occur, we know that implementing retries means duplicates can and will occur. Because we know things are going to fail, and because we know retrying something is something we are going to try as a solution, we are going to pretty much explicitly tell our code, hey, we're going to introduce duplicates into our system. We're going to re-invoke an event. We're going to retry this API call. We are going to do it again. And because we are the ones that know that we are introducing these duplicates into the system, we need to be mindful of that fact. We need to be mindful that duplicates can and will occur if we are going to use retries in any form or fashion. So if duplicates exist, then idempotency is key to mitigate some side effects. So side effects. Who has dealt with side effects in an application that they did not want to deal with? Yes. Side effects. We're going to talk about the most detrimental one when it comes to idempotency and when you build something when there is no idempotency. So what happens without idempotency? So my husband and I are driving home, and we're coming home from a road trip, and I, like I normally do, get a hankering for cake, because if there's something you have to know about me is that I love sweets, and I will always have cake whenever I can. And so as we're driving home, I open up Fried's, which is a very popular bakery in Las Vegas, which is where I'm based, and I decide to place an order. And I'm taking a look, and I'm looking, everything looks really good, but who am I kidding? I'm going to order the world-famous strawberry shortcake. So I start going, and I place my order. So as I place my order, a couple things happen. I'm not paying attention because I'm so excited. I'm placing in my order, filling out my details, talking to my husband about the great time that we just had from our camping trip. And we have to see what happens now. What happens to that order that I have just placed? So we set some boundaries here. In this, there's going to be me, there's going to be the website, the Fried's website, and presumably there's going to be an API. And behind the rest, all of this, there could be other services. Maybe they have an ordering service, maybe they have some other services that are behind there, but we don't care about that right now. We're just going to deal with these three. And direction of time flows downward. So when I place my order, the order is placed, and it is right about this time that I enter the tunnel. So unbeknownst to me, I'm just thinking, I'm just not really thinking about it. I'm just placing my order and talking to my husband. So at this point, network failure occurs because we're pretty deep in the tunnel. And this happens very, very often. This is a very clear, explicit example, right? I go into the tunnel, I lose signal. And at this point, the order is actually processed. So Fried's is creating that cake. They are going through, mixing everything together, and they have acknowledged that they're going to process my order. But because I'm going through the tunnel, there's no way for me to receive that. There's no way for me to know that this order has been processed. I'm just looking at my phone and going, oh, well, maybe I'm seeing a little spinning timer, or maybe I'm seeing that it's still trying to connect. And so when I exit the tunnel, I think everything is okay. Presumably, when I regain network access after exiting that tunnel, one of two things is going to happen. I'm either going to see properly that it has not gone through, or I'm going to see that it's properly gone through if it's a really, really bad implementation. But most likely, I'm going to see that, oh, there's an error of some sort. It didn't go through. Maybe there's a socket error. Maybe there's a connection timeout. I'm going to see that it didn't go through. And so me, being the cake addict that I am, I'm going to get my cake. So I'm going to go place an order again, right? And I'm going to place that order. I'm going to process that order. And cake is on the way. So if you've worked with this before, or if you've worked with any kind of distributed system, you can probably see where the really big side effect is going to happen right now. But if you don't, let's zoom out a bit. Let's take a look at what has actually transpired. Because this first order, the one that I placed before going into the tunnel, that is still a valid request. That is still being processed. That cake is still being made. And so I'm going to get this cake, but I'm also going to get this first cake. And so a lot of people are going to say, well, Adrienne, 2 cakes are not really a problem. A lot of people might agree that, oh, 2 cakes, that's great. But think about the other, more potent side effects of that. You're paying for 2 cakes. You are billing somebody twice. You are getting 2 things that you don't really need 2 things of, cake included. So what this really shows is that the intent of my request, the initial one, my intent was that I wanted a single world-famous Fried's strawberry shortcake. And instead, I got 2. And at this point, the API, where whatever Fried's is using in their system, because there's no idempotency built in, it has to take these requests at face value. There's no way for it to tell that I'm not some cake-eating monster and is like, yeah, she wants 2 cakes, so we're going to give her 2 cakes. It's going to take both of these requests, and it's going to say these are both valid requests, because there's no way for it to understand the intent that I am trying to say, which is I want a single cake. And that is the biggest side effect of building an application or building a distributed system without idempotency built in if it warrants it. Duplicate requests are considered valid requests. So just like I said, if you don't think 2 cakes are a problem, think about the other side effects of doing things more than once when you don't intend to. That's a pretty harmful side effect, and it all boils down to the intent of your request is not captured. So then how do we apply idempotency, Adrienne? Even though I really want 2 cakes, how do we apply idempotency so that this doesn't happen? Well, there are a few elements of idempotency that need to be part of your requests or part of your system so that it can understand the intent. So the first thing that you need is some sort of idempotency key. So this is usually some sort of unique identifier. This is something that captures the intent, and it's derived from the caller. So this could be a hash of parameters, it could be an ID, it could be an event ID, a client token. It's a UUID. But it's a way for us to know what these different requests are, to distinguish them between each other. Next is an idempotency layer. So now that we have a way to distinguish the different requests that come in, the next thing we need is a way to deal with them. What do we do now that we know the intent of our request? This layer is now what we use to kind of act like a filter. And this is what we decide what to do. So in our example of this web request, this could be at the API layer where it's deciding what to do. If this is in a queuing system, this could be on the consumer end. This is where it's going to decide what to do with that intent. And finally, we need a persistent store. So not only do we have the intent captured now in the key, not only do we have a layer with which to do something with it, we now need a place to actually store some information so that we can process these requests and actually deal with the intent that we are capturing. So for this to work and for the idempotency keys to have any meaning, we need to have this storage somewhere. And this stores the state. This is going to be the source of truth for us. This helps us understand, and if we are going into more complex workflows, if you've ever used durable functions before, you can do something like going back to a checkpoint at a point of failure and actually retry your request safely because it can rerun all of the steps that it has captured so far. But it can only do that if you keep a log of what has actually occurred up until the point of failure. So if those 3 pieces exist, then we can actually build something in an idempotent way. So if we go back to the example that we have, let's see how building idempotency into it will actually save our requests and make it more idempotent. So we have me, right? We have me on my phone wanting to get that cake. And now it's already here that we're changing something. Let's say we are able to consult for Fried's and to help them get their systems into a more idempotent state. So here we're going to generate some sort of unique identifier. And like I said before, it just needs to be some sort of unique ID. Maybe it's something like this. And maybe it goes into our place order event this time. So we place that order. It is generating a unique ID. And now we have two new things here. Well, maybe just one, a persistent store. So this still goes to the API, and we now have a persistent store where we are going to now store that key. So when I now send this request and I send my order, I'm going to go, and instead of going directly to place the order and have the order processed and have it go directly, we need to go check something first. We're going to go to our persistent store and say, hey, there's this key that I got. Have we seen this before? Is this a valid request? Is this something that we've already done or not? And so we go to the persistent store, we check it. If there's nothing found, then we can safely assume that we can run this place order event. It's something we haven't done before based on our source of truth, and so we can go ahead and run that event. Once it has completed, whether or not it's a failure or a success, we will now set that idempotency key as well as the result of what has happened in that place order event. We're going to store it because we now know that we have processed this particular event. So now, this initial request is way more idempotent, and I think you can understand why this is way more helpful than the last one. So let's say we continue on with the previous example where I was going through the tunnel. And let's say the same thing happened, but this time this idempotent request has run. So when the response was not received by me, and I am like, oh no, I need my cake, I'm gonna go place the order again. Let's say I do go through and get click heavy and place that order. It's gonna go now and say, hey, do we see this idempotency key? And this time it's going to exist. This time it's going to know this is the same cake addict that is requesting it, and she's ordering the same thing, and we've already processed it, and let's send that response back to the client. And even if we have multiple subsequent requests, whether that's me clicking on it, and we can talk about why that shouldn't even be allowed, but even if it's the system itself that is doing these subsequent retries for you in an automated fashion, it's still going to be okay because it's going to check against the persistent store. It's going to see that particular event ID or idempotency key, whichever one that you're using, and it's going to know that this intent, this has been captured and has already been processed. And in a nutshell, this is a very, very simplified way of showing you how idempotency works. There are a lot more complicated workflows that could occur. This is where you can try things in retries like jitter rates or setting timeouts on how often you retry something. This is where, if you need to, you might have to lock the database in order to ensure idempotency. But at a high level, the three elements that I've shared with you are the things that you would need to complete idempotent requests in your systems. So now, using that as a framework, I want to share with you some of the libraries and tools that I have found that kind of show this in action and actually use this and support this and want you to use it in the same way. So the top one that I found, and this is not because I'm an AWS fanatic, I actually like Microsoft's ecosystem a lot better, but AWS Labs has something called the AWS Lambda Power Tools. And this has it for Java, Python, which is great. This is what they had prior. And they've recently introduced TypeScript and .NET. .NET has a very big asterisk because it is not production ready. So they're working on it. They have a roadmap that you can check out. And they are very, very open and transparent about what is happening, what you should use, what you should not use, and what is going to be slated next for the team to work on. So I really like this particular library because it uses a lot of the things that I spoke to you about. They use an idempotency key. In this case, they use a hash representation of the entire event, or you can choose to configure a specific subset of that event. So if you want to use the whole payload, if you have really, really small payloads, then that might work for you, or if you only need a couple things, then you can choose to use that. Persistent storage, of course, it's going to be DynamoDB, and at the time, still right now, checked yesterday, this is the only persistent storage that is supported right now. So you can see here as an example, this is how you can quickly set up an idempotent request with an idempotent decorator, which is right here on line 8. So you're not only having the DynamoDB persistence layer that is here, and you set the persistence layer to that particular DynamoDB instance, but you also have the idempotent decorator here on the function. The features that are really, really cool about this is that it prevents multiple Lambda handler function executions already for you, so it's kind of built in. If it's on the same payload and it's during the same time window that you can set, then it will do that check for you. It will prevent it happening for you. So you can set it to maybe like an hour or maybe 30 minutes, depending on what you need. You can configure what that time window is, what that constraint is to check whether or not it's a duplicate request. You also have a really cool feature that ensures that the Lambda handler will return the same result when it's called with the same payload. So again, another very basic check that should be checked often is already built in for you. And it reuses the same DynamoDB table to store idempotency state. So that source of truth that I was talking about, that persistent storage layer, this is where that comes into play. The function name is added in addition to the idempotency key as a hash key, and that's really, really useful for when you want to retry something and retry from checkpoints. So again, I'm gonna go back to the comparison with durable functions in Azure, where they have an orchestrator that really is the organizer. They're like the air traffic controller of all the functions that you are doing. And they always go through and check against an Azure storage table, which is an append-only log of everything that has occurred. And this is very, very useful and is used in the same way so that if at any point there's a failure, it can go, hey, let's retry this. Okay, this was successful. Let's retry this, retry this, retry this. And so understanding that it's going to retry it in this fashion means that you have to kind of make these functions deterministic. And lastly, you can set an expiration period for idempotency records. So this is really, really important because you are storing all of these keys. You are storing all of these results, presumably. And if you work at the scale that some developers do, that is going to grow really, really, really large. And you don't need all of those keys all the time. So setting an expiration period is helpful because usually you only want or need those keys. You need to check it maybe for every hour, maybe for a day, and this will help you cut down on how much storage you're actually using and how large that persistent storage layer will actually grow. So that's my favorite one that really encourages idempotency and maps very closely to what I've showed you today. The other great tools and libraries that exist, number one, you can't talk about idempotency without the Stripe API being mentioned. So they support idempotent requests and they implement idempotency keys. So you can check out their blog post as well as their documentation on how they run idempotent requests. This has been very well done. People love the Stripe API because of the way that they've supported idempotency in this way, and it's always been pointed to as a resource whenever you want to start looking at idempotent requests. There is Idempotent API, so this performs additional idempotency checks and is a NuGet package. There's a great blog post from .NET Nakama here that actually talks about how you would use this in a .NET package or .NET application. Then there are step functions and durable functions, like I mentioned. So these are not necessarily idempotency focused, but they do play hand in hand with the thought of idempotency and making sure the requests that you run or the functions that you run are done in a very deterministic way. And it also builds in the checks for you so that you don't rerun requests and have those duplicate requests as side effects. And lastly, Cisco APIs. There are a few, not all, but there are a few that do support idempotent post, delete, and put requests. So some of those are the Intersite API as well as the Meraki API. So these are other great tools and libraries where you can see how they have implemented idempotency. And again, they will fall within the same range of the 3 elements that I've shared with you today. And with that, I want to thank you, NDC London. It was very short, but the goal of this talk was whenever people talk about really big words, fancy words, I want to make sure that it's so simple that you can understand it, that at the end of it, you can say, oh, that's what it means. And now you can go on and presumably share this with someone because you are now well informed. So thank you so much, NDC London. I'm happy to answer any questions.